to the last lecture in this course. This is a lecture that I wrote over the weekend. It's the first time I'm teaching the Hawking effect. I used to avoid it because nobody really knows anything for sure in that area. It's quite depressing, but it's not so surprising because it's an instance where we try to combine strong gravity with quantum field theory. And so really, to do it properly, we would need quantum gravity. So I've pulled together the arguments that I think are the strongest, but even they are not on entirely strong ground, not as strong anyway as what we did for cosmology. So let's look at the Hawking effect. In 1915, Schwarzschild, who was in the First World War at the time and was just about to die like a month later, Schwarzschild came up with that solution to the Einstein equation and sent it to Einstein. So this is describing a static black hole without charge, without angular momentum. And this is the representation of that black hole solution in the so-called Schwarzschild coordinates, the way that Schwarzschild first found them. We recognize that things blow up in two places. One is as r is equal to 0, this blows up, that blows up, and indeed it is a true singularity. Although perhaps not a singularity of the kind that people usually imagine. I'll say something about that a little later. Basically, it's a space-like singularity, not a time-like one. But it's a true singularity. Curvature blows up there. The curvature invariants are divergent there. And then we have that this representation of the metric, and by that I mean in this coordinate system, the metric also blows up when r is equal to 2m, because then this whole thing is 0, and we have to take the inverse of it. So that blows up there. This is not a singularity. This is, well, mathematically it is, but it is not, as far as the physics is concerned. This is only a horizon, but not a singularity. There are other coordinate systems, and we will see one later on, in which we see that the metric really is completely smooth across the horizon. And therefore, the physics is really smooth. For example, the curvature invariants are perfectly smooth across the horizon, r equal to m. So r equal to m comes up all the time. Just keep in mind 2m is the size of the horizon, is the location of the horizon. So the coordinate system consisting of t, r, phi, and theta is called the Schwarzschild coordinate system. Now remember that the very same space-time can be expressed in any number of coordinate systems, and that's what we will do. We will not change the space-time in what we do throughout this lecture today, but we will change occasionally the way that it is represented. We change the coordinate system. The Schwarzschild solution was initially, for many years, studied in these coordinates, and that has led to a lot of misunderstandings. In particular, it used to be thought that there's a singularity at r equal to m, and that is, of course, not the case. But there's something else that is weird about the Schwarzschild coordinates. Namely, remember that in the Schwarzschild coordinates, the Schwarzschild space-time has a sign flip here as you cross the horizon, right? Because this is changing sign, that is changing sign, as r goes from larger than 2m to smaller than 2m. So therefore, while usually far away from the black hole, this is a small number, and therefore that is basically 1 minus a little bit. This is positive, as it should be, and then the radial variable has this positive, but with a minus sign. It is giving you the usual signature of the Minkowski metric, a +1 for time and then -1 for the three space directions. This is, after all, just the usual angular variables, theta and phi. But if you go to the region in the coordinate system where r is smaller than 2m, then the prefactor in front of the dt squared becomes negative, and the prefactor in front of the dr squared becomes positive, which means that the covariant vector dt becomes space-like inside the horizon, and the covariant vector dr becomes time-like inside the horizon. And that really messes up intuition. Let me show you exactly how it does that. Consider, for example, a traveler, let's call her Alice, who is freely falling from a distance of, from a Schwarzschild distance, r0, to r equals 0. So Alice goes on a big adventure. She's falling into the black hole. Remember that the Schwarzschild distance is not like proper distance at all. It's just a distance according to the Schwarzschild coordinate system. So Alice starts out at r0. This is where the location of the horizon is, at r equal to 2m. And here is the exact trajectory that Alice will undergo as she falls towards the black hole, crosses the horizon, and eventually reaches the singularity. So Alice will free fall like this. This is the Schwarzschild time variable. She will free fall like this. She will accelerate. And as it happens, she will eventually asymptotically approach the horizon. As far as the Schwarzschild coordinate system is concerned, it will take her all the way up to t positive infinity to approach the horizon. But really, she does make it across the horizon at finite eigentime. I have also here I give you the equation for the eigentime as well. It only takes her a finite eigentime to go all the way to up to infinity there, and then she continues on the other side of the horizon, and she comes down like that. Notice that the Schwarzschild time actually is decreasing. As she's inside the black hole, her Schwarzschild time goes down as her radial distance is approaching the singularity, and eventually she hits the singularity there. Now that shouldn't be too surprising, because inside the horizon, the radial variable plays the role of the time. She's really forced to go in this direction here, for radius going to 0, for the same reason that we are forced to go forward in time. The radius becomes the time variable. So she has to go this way. Whereas if she has engines in her spacecraft, she can actually choose to go up and down in time as she wants. That's just the Schwarzschild time. The Schwarzschild time is not a time variable inside the horizon. It simply isn't at all. It's not just a weird time variable. It just isn't a time variable because it's really space-like. So clearly, if we want to do quantum field theory on a Schwarzschild black hole background, we might be well advised to use a different coordinate system. This doesn't seem very intuitive or practical. It's just historically how the solution was first found. But you may want to play around with those trajectories there. It's just nice to actually plot curves like this to get some intuition for this. I'm still waiting for a video game that implements all that stuff. Okay, so we need better coordinate systems for the quantization. First, we'll adopt a simplification. For now, we will drop the angles. We will drop the angle variables. We will just care about radius and time, because that makes things two-dimensional, and we can use simplifications that come along with that. And eventually, I will tell you then what happens when you restore the full 3+1 dimensionality of it. So let us design a better coordinate system. Let us design a coordinate system of the kind that Alice would find useful. Let's say Alice starts her adventure at the horizon, and from the horizon she then goes free falling into the black hole. So the R0 is 2m. R0 was the initial radial position of Alice. Now, what kind of coordinate system for the entire space-time would Alice appreciate? Well, first of all, she would prefer to have a metric, to have a coordinate system in which the metric is given by regular functions, where the entries of the metric are regular across the horizon. Also, Alice would like to have a coordinate system which is at her initial position a Riemann normal coordinate system. Later we'll have to say how we extend it, but we want that, or Alice would appreciate to have a coordinate system in which the metric at her initial location is eta mu nu. So let's say at her initial location, which is at the Schwarzschild radius, at the horizon itself, which is exactly where, of course, the Schwarzschild representation of the space-time was singular, Alice says, no, 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 I want the metric to take the usual Minkowski form right at the horizon. And she writes to request that, because if it is true that there is no singularity at the horizon, then as everywhere on a Lorentzian manifold, you can always find a coordinate system such that locally the metric takes the representation eta mu nu. So why not asking for that right at the heart of it, at the horizon? So let's say Alice wants that. She wants that the metric takes the form eta mu nu right at the horizon. And then it can deviate, of course, from that, and it will deviate because there's curvature and so on. It will deviate from that away from the horizon. So this should be possible if it's true, as I promised, that there is no singularity at the horizon. But this only fixes, so far, this only fixes what the coordinate system should do close to the horizon. What should it do elsewhere? Well, let us ask that the metric takes the form of a conformal prefactor times the Minkowski metric everywhere. If we get away with that. Now, in 2 dimensions, we will. Now, that has a huge advantage because, if you remember, we showed that if a metric is conformally related to the Minkowski metric, then we immediately know what the action looks like. And the action won't have the F in it, neither will the equations of motion. And we can write down the quantum field theory, and we can solve the 3 conditions, namely hermeticity, equation of motion, and canonical commutation relations right away. So if we succeed in finding a coordinate system that obeys those conditions, then that will be great. Alice can do the quantization of the field theory and can write down the solutions right away. In fact, Alice can also, she can solve the quantum field theory to the extent that she can write down the field as a function of operators and mode functions and everything. And she can even identify which state in the Hilbert space would be what she calls the vacuum. Because she knows what the positive and the negative frequency modes are, and all this discussion that we did throughout this course can be applied in this case. So it boils down to finding a coordinate system that obeys those conditions of giving us the metric in the form of eta mu nu at the horizon and a conformal multiple of it elsewhere. Can it be done? Well, yes. Alice's choice are the so-called Kruskal-Szekeres coordinates. And let's call those coordinates capital T and capital R. Now, if that's simply another coordinate system for the same space-time, then there must be a bijective map between the Schwarzschild coordinates and the new Kruskal coordinates. And here it is. Unfortunately, in the literature, you'll find it in pieces. I just put it together for you so that you have all in one place. Also, most treatments of this will tell you about how to derive all of this. And it goes on for pages and pages, and then you lose easily the overview about what's going on. So I'm focusing here not on the derivation of the technical details. I'm just claiming this is how it is, and then you can check yourself. For example, I'm claiming here that this is the transformation from the Schwarzschild coordinates little t, little r, to the Kruskal coordinates capital T, capital R. And you can check for yourself quite easily whether, it's a little tedious, but you can do it, straightforward. You can check whether when you take that transformation and apply it to the metric tensor, that you get a metric tensor of the desired kind. So instead of deriving it, let me just do it the mathematician's way and just claim it and leave you to prove it. Okay, so this is the transformation between the little r and little t Schwarzschild coordinates and the Kruskal coordinates capital T, capital R. And the claim is that if you do that transformation and carefully transform, therefore, the metric as a covariant symmetric 2 tensor, then this is how the metric looks like afterwards.
Is the theta the step function?
Yes, it is. It is the Heaviside step function. That's right. So what this is saying is that outside the horizon, it's these two terms, and inside the horizon, it's those two terms. Depends what's bigger, 2m or r. And you might think that there's a discontinuity here between inside and outside the horizon because, once it's the sinh, in the other case it's the cosh, but there's no singularity here. There's no discontinuity here. The reason being that when r is equal to 2m, this prefactor goes to 0 here. So it's all smooth. Okay, so what you get is that the metric takes this form here. And this is the desired form. It has the metric eta mu nu of Minkowski space here, dt squared minus dr squared. And it has this prefactor, which is just a conformer, just a function in front of the metric. And this conformer prefactor obeys the condition that it becomes 1 on the horizon. One moment. It's 1 on the horizon. Let's check that. The horizon is where r is equal to 2m. If r is equal to 2m, then that is e to the power of 0. So that's a 1. And here we have 2m divided by 2m. You see, in this equation, in principle, this metric is a rather complicated expression because you would have to express the little r, the Schwarzschild coordinate, in terms of the capital T and capital R, which is possible because that map is invertible, but it would be extremely tedious. I'm actually not sure it can be done in a closed form. But in principle, it is invertible, as you can check, by just calculating the Jacobian and its determinant and checking that it's non-zero. So this is really 1 on the horizon. So at the horizon, you really just have the Minkowski metric. So you're really in a co-moving, you're really co-moving there with Alice. And other than that, you have this structure here, which is guaranteeing that in this coordinate system, Alice will find that light will travel at 45 degrees. Light cones are still going the same shape. Yep.
So at r equals 2m, both coordinates always 0, 0, right? So like t equals 0, capital T equals 0, capital R equals 0. So is there some subtlety here that we've contracted all of the t dependence to a point?
Yes, and we will later see it in the plot. Yeah. If you remember, we had a similar feature in the previous lecture with the accelerated observer. Okay, so in this new coordinate system, it would be very easy for Alice to keep track of what light is doing and so on. So here is now a plot of how the Schwarzschild space-time looks like in these Kruskal coordinates. So here we have the Kruskal space direction, Kruskal time direction. And remember that in the Kruskal coordinates, we have that that the metric is just proportional to eta mu nu with a positive prefactor. So there is never a change of sign in front of this or in front of that. So r is always space-like. T is also everywhere time-like. They don't change character. Okay, so here's how it looks like, the space-time in these Kruskal coordinates. Space this way, time that way. And all of Minkowski space is this half. It's just this half. There's nothing down here. It turns out that the space-time could be extended this way analytically, but I'm not caring about this here because I want to describe the real world. And this lower part would describe a white hole, a hole out of which only stuff can come out. And this is not how black holes operate. And they don't have that. So the actual Schwarzschild solution of just a black hole is given by this half of R2. And I'm plotting here several things. One is the event horizon. The event horizon is here. That's the horizon of our black hole. The singularity turns out to be given by this hyperbola here. Remember that the metric in these Kruskal coordinates is proportional to eta mu nu, which means light cones look like this, 45 degrees, everywhere. All the light cones look like this. Now, in this coordinate system, Alice is falling straight towards the black hole, straight towards the black hole singularity there. Alice might have a friend who says, Alice, wait a moment, I'm coming along too, and that adventurous friend is also going that way. Some other friend is a chicken, he just goes close to the black hole and then changes his mind and goes away again, okay? Now the thing is though that Alice and her friend are not necessarily meeting up. See, it's easy to think that maybe the singularity in the center of the black hole is like a point in space where everything is crushed into a point, and then that point in space persists in time. That's not how it is. What we see in this picture is that the singularity here is a hyperbola, and look at the slope of it. It's less than 45 degrees everywhere. The singularity is actually space-like. So it's not some point in space that persists in time. It's more like a region in space and time ends. That's what it is. I've also, for illustration, drawn here some indication of what the Schwarzschild coordinates are in comparison. So the Schwarzschild coordinates are such that constant timelines are like this. They all meet at the origin. So this is a constant time, that's a constant Schwarzschild time, that's a constant Schwarzschild time. And a constant Schwarzschild radius is one of those hyperbolas here. That's constant radius, all these hyperbolas. And also that is a constant radius hyperbola for Schwarzschild spacetime. Remember though that R is not a space-like coordinate inside the horizon. So in practice, if you are here outside the black hole, then you must travel upwards because all light cones look like this, and you must travel with an opening angle, so your tangent, the tangent to your world light, has to be somewhere between this and that. It's just like ordinary Minkowski space in that regard. So you can travel like this as long as your slope is never, more shallow than 45 degrees in either direction. Which is why this is a horizon here, right? If you go this way, you hit the horizon. But if you are, let's say, there, let's say you are inside, and you wanted to go outside, you can't, because remember the light cones are everywhere like this, because the metric is proportional to eta mu nu. So the light cones are everywhere like that, even if you're inside. So you're here, let's say, this would be your light cone, and how are you going to make it outside? You can't, right? Because you can only, the shallowest you can go towards the right would be this way, but that's not getting you out of the black hole. You can only approach, you can only get closer to the horizon there, but you could never cross it back again. Okay, and you see how the Schwarzschild time variable is singular at that point compared to the Kruskal coordinates. All right, so this is, I suppose, a coordinate system that's much more plausible from Alice's perspective. Oh, by the way, and the singularity itself, the singularity up here, is given by a hyperbola whose equation is this one, by the way, namely that T of R is equal to the square root of R squared plus 16m squared over E. Now, these were Alice's Kruskal-Szekeres coordinates. Just a sec. She can also now introduce light cone coordinates.
So at the singularity, is it just the Schwarzschild of the time that ends, or also the proper time of the
in the Kruskal coordinate system, there is no final time. You see, the T can go, capital T can grow arbitrarily large, but not if you're coming that way. You have to go this way, and you can have arbitrarily large T's. And similarly with the R, the R can also go arbitrarily far negative, arbitrarily far positive. But in this RT diagram, there is an end to time, right? So you can only go that far, and then that's the end of the world as far as you're concerned at that point. Yeah, it turns out that the manifold cannot be extended beyond that singularity. And my comment previously was that actually, mathematically, you can analytically extend the space-time beyond that line. You can. But that would give you a very highly symmetric solution, and nature is not going to do this. In fact, when you have an actual black hole that's created from stellar collapse, for example, would not, of course, have anything like a white hole solution at the bottom there. Those of you who are familiar with the Penrose diagrams will recognize that the usual Penrose diagrams that are given for a black hole are very similar to this. All you do in order to get that is that you further use the conformal factor to squeeze everything so that you get a finite description of it, whereas here R and T go all the way to infinity and minus infinity. You can use another conformal factor to get a space-time that is not the same space-time. It's not Schwarzschild space-time, but it's one which has the same causal structure, because a conformal transformation will not change the direction of the light cones. And so you shrink everything to finite size. This left-hand side is usually dropped. And then you see that this is the usual picture. If all of that is shrunk down from the right, from the top, you get the usual Penrose diagram. But I didn't want to introduce yet something new. I tried to keep things I tried to introduce only as few things as possible so that the arguments for the black hole radiation are as elementary as possible. Okay. So Alice has a nice coordinate system, the Kruskal coordinate system, but in order to make it even better adapted to for the solving of wave equations, she may want to use light cone coordinates. And she does it the usual way. There's a light cone coordinate u, which is t minus r, and another one that's t plus r. In that case, the metric takes this form. It's the conformal prefactor times du dv, the same way we had it on Friday. And again, this is the same prefactor that we had earlier, just in the new coordinates there. You see, if r goes to 2m when we are at the horizon, this becomes 1, this becomes 1, and this becomes du dv. If you remember, du dv is the usual Minkowski metric, but in light cone coordinates, with a 0, 1/2, 1/2, 0 as its entries. So this is the light cone version of the Minkowski metric, and that's just a conformal prefactor. Then, the action, which can always be written in this form, the Klein-Gordon action, which can always be written in this form, takes that form if we write it in terms of t and r, and if we write it in terms of u and v, then it takes that form. It turns out that we have some restrictions on the integrations here. Actually, this is a double integral. That's a double integral as well. We have that capital T is larger than minus r. This is the restriction that we are only looking at this part. This is the Schwarzschild solution. So this is to say that T is larger than minus r because this line is the line T is equal to minus r. Okay, T equal to minus r is also the line u equals 0. Yeah, because u is T plus r. T minus r. So what we have is that u is larger than, so we have that T is larger than minus r is the restriction on the integrals in the action here. And the condition on the u and the v integrals, once we write the Klein-Gordon equation in terms of the u and the v coordinate system, is that the v can be integrated all the way from minus infinity to plus infinity, but the u has to be restricted from, or the v has to be restricted from 0 to infinity only to get just the Schwarzschild solution. That is a bit of a difference to what we had previously on Friday, when we just looked at an accelerated coordinate system. Because if you remember, the accelerated coordinate system had two horizons. The accelerated coordinate system had all of this here, this and that. It had two horizons. It has a future horizon. It has a past horizon. There was the future. There was all those events that the accelerated observer could not influence. And there was the past horizon beyond which were events that could not possibly influence our observer. Here it's different, right? Because we don't have a past horizon, we only have a future horizon. And that little difference will come back later when we have to identify what the vacuum state is. There's a little difference between the acceleration case and the black hole case because the acceleration case has two horizons. The black hole case is only one horizon. Only a black hole horizon, no white hole horizon. We have never seen a black hole that would have a white hole along with it. So there is a bit of a difference. Okay, so Alice chooses not only the RT coordinate system, she will also like to use the U and V coordinate system because, if you remember, in the UV coordinate system, oh, and by the way, remember why it is that all those complicated prefactors don't show up in these actions? It was because of conformal symmetry of the action in 2 dimensions. Whenever you have an action in 2 dimensions and you change the metric by a conformal prefactor, you're not changing the action at all. It looks just like before. So this action is conformally equivalent to the Minkowski metric. That's why there is no prefactor. It just cancels out because of the measure factor and the factor by which the g mu nu changes cancels out. So the action is very simple here, the action is very simple there. It doesn't, by the way, mean that the physics is completely the same. It couldn't be. Just like when we discussed on Friday, the case of acceleration. Of course, when you're accelerated, then physics is different for you. It's just that in this coordinate system, light still travels at 45 degrees. But if you were to choose to look at objects that have a mass, then of course they would no longer travel on straight lines. They would very much show that they go with this typical parabola of, being accelerated, or hyperbola. It's just that the massless case is so easy in this case. Anyway, so the advantage of using the light cone coordinate system for Alice is that she can also completely solve the problem right away, because the equation of motion that comes with this, the Euler-Lagrange equation for that action, is simply du dv of phi equal to 0, which can easily be solved as we did. And we find the solution for the quantum field theory, as usual, to be like this. The phi as a function of u and v is given by mode functions times creation and annihilation operators. And we have that for left movers and for right movers. So I'm just writing here the right movers. The left movers can be inferred by symmetry. There you would have the v instead of the u. See, the u are t minus r, the v are t plus r, and so you get the left and the right movers. All right, so for simplicity, I would not spell out exactly what the right movers are. Now, left and right movers, in the case of the black hole, should really instead be called infalling and outgoing. So it's the ingoing and outgoing. Left movers are where r is diminishing. So that means ingoing. It could be, of course, from both sides of the black hole, right? But the radius is a positive variable. So left moving means ingoing. Right movers are outgoing. All right, so Alice solves her quantum field theory, and that's the solution. Remember that this is just omega times t minus r, and that's what you would usually have. It's easily translatable between the t's and the r's and the u's and the v's and so on. So then, what would Alice call the vacuum state? Now, for Alice, as she crosses remember, as she crosses the horizon, g mu nu is eta mu nu. It's like in a freely falling elevator or something like that. So she doesn't locally see anything special going on. Now, if her detectors are not clicking, then she would say the state of the field is what she would call zero Alice. And it's the state that's annihilated by her A operators, by these guys. So it would seem that this is a plausible solution. We have a solution to the quantum field theory. We have a candidate for what the vacuum might be. We have good reasons to think that this is what Alice would see and do and declare to be the vacuum state. And in any case, when she crosses the horizon, why should there be something special at the horizon? By the equivalence principle, everything should be smooth. Maybe that should be the vacuum state. We'll come back to that later. For now, let's consider that this coordinate system is not good for everybody. It's good for Alice, but it's not good for everybody. Let's say there is somebody, let's call him Bob, who has no intention of going into the black hole. Instead, Bob is very far away, asymptotically far away. And Bob also does quantum field theory. Now, would Bob use Alice's coordinate system? Unlikely, because look at what her coordinate system does where Bob is. See, that's her coordinate system. Her metric looks like this. And this metric basically goes away where Bob is. It diminishes. See, if r is very large, then e to the power of minus a large number, that's very small. And if r is very large, this is also small. The whole thing is very small. It's a very, very compressed way of writing things. This is certainly not a natural coordinate system for Bob. Not only would the metric look like a very, very small tensor there where Bob is, but it keeps diminishing exponentially fast. Bob wouldn't do his physics in that coordinate system naturally. In other words, if he has detectors, they wouldn't couple to the usual way when you use that coordinate system. They wouldn't couple to the field the usual way if you use that coordinate system. So what coordinate system might Bob want to use? Okay, so Bob's choice of coordinate system. Bob is far away from the black hole. He wants a coordinate system in which the metric is basically the Minkowski metric. Now, that's always possible, of course, because the space-time is not supposed to be singular, except at the singularity. So you can always find a coordinate system such that's true. But in fact, he wants it to be true, in large areas, because he's far away from curvature. So he can afford to ask for that. So we want that the metric goes into the eta mu nu Minkowski metric far away. So that's a requirement that Bob would have. But that only fixes what the metric is supposed to look like far away. What do we want the metric to do elsewhere, especially close to the black hole? Now, Bob will say, okay, I want to do what Alice does. I want to have a coordinate system that not only looks like makes the metric look like Minkowski metric where I am. I want the metric to be conformally flat, obviously, explicitly conformally flat everywhere, for the same reasons that Alice required that. Namely, he wants a coordinate system in which photons travel at 45 degrees, so the causal structure is still the usual one, and so that we know how to write down the action, the Klein-Gordon equation, the mode functions, the solutions to the quantum field theory. So can he do that? Can Bob find a coordinate system such that the Schwarzschild spacetime has a metric which becomes this metric far out, and elsewhere, close to the black hole, takes this form? It's explicitly conformally related to eta mu nu. It turns out Bob can do it, and this coordinate system is called the tortoise coordinate system. Let's call this tortoise coordinate system T star and R star. And here's the transformation. The transformation from the Schwarzschild coordinates is that the Schwarzschild coordinate is also Bob's time coordinate, which is perhaps not surprising because far out, the Schwarzschild time ought to be Bob's time, because far out, the Schwarzschild coordinates treat the time as, it has this prefactor, but that prefactor becomes 1 far out. So it is quite plausible that the Schwarzschild time is Bob's time. This wasn't a derivation where I just said, I'm just saying it's plausible that the Schwarzschild time matches the wristwatch of a Bob who's far away. But also, we want that the other conditions are fulfilled, and for that, we need that the radial variable is transformed into a variable R star, which is given by this expression here. Now notice that there's something fishy about that expression, which is that it involves the logarithm of R over 2m minus 1. And, well, that better be positive here. That better be positive. So this transformation only works outside the horizon. So Bob can get away with his demands. He can have a metric which is the Minkowski metric far out, and which is conformally related to the Minkowski metric everywhere else, except inside the black hole. There we cannot have it. The coordinate system can only go as far as the horizon. Remember, this is a bit similar to what we had with the accelerated observer on Friday, who is also who has a coordinate system that doesn't cover all of Minkowski space. And so the coordinate system of Bob is not covering all of the black hole space-time. It's only covering it up to the horizon. So what then is the metric in Bob's coordinates? So in Bob's coordinates, the metric is given by the eta mu nu of Minkowski space, as desired, multiplied with this conformal prefactor, and that's what it looks like. And you notice that this thing goes to 0 as R goes to m. But far out, as R goes to infinity, where Bob is, this R is very large, that term goes away, and we just have the Minkowski metric as was desired. So by design, that's what the metric looks like then. That's the best you can do. It's the only thing you can do if you want the metric to become the flat metric far away and to be conformally related otherwise. Okay, so Bob has a coordinate system. How does the Schwarzschild spacetime look for him? At least the outside of the black hole. Because remember, his coordinate system doesn't even cover the inside. So Bob has a coordinate system with coordinates r star and t star. And for Bob, all the light cones are at 45 degrees, because for him too, the metric is just a conformal multiple times eta. Therefore, light cones are at 45 degrees. Therefore, a freely falling observer, well, let's just say first, any traveler would be able to travel any trajectory like this, some serpentine curve if you want, as long as the slope is nowhere shallower than 45 degrees. Now, large r star mean far away from the black hole. It's perhaps not easy to see here. This radial coordinate is such that for very large r, also r star is large. You see, r star is given by r minus 2m, which is a constant. And then you have here this expression where when r goes very large, this also increases. Slowly, but it does increase. So overall, r star, it turns out, is a monotonically increasing function of r. So it's just a rescaling of the r variable, except that r star is actually 0 at the horizon. Sorry, no. No, it's not 0 at the horizon. Let me see. The horizon is at minus infinity. So it's still true that it is a monotonically increasing function of r, but the horizon is shifted all the way to r star equal to minus infinity. See, if r goes close to 2m, then we have here a number that's a little bit larger than 1. It approaches 1 ever more closely. Minus 1 means you have the log of an ever smaller number, which means that this log goes very, very negative, right? So what you get is that as you approach the horizon, r star goes to minus infinity. All right, so what this means is that for Bob, the coordinate system looks like this. R star ranges all the way to plus infinity, which is infinitely far away from the black hole. And then all the way over there to minus infinity, r star going to minus infinity, that's where the horizon would be, at minus infinity. And the traveler could travel here at most with an angle of 45 degrees. A free-falling traveler would accelerate in this way. Therefore, the trajectory becomes closer and closer to 45 degrees because it's faster and faster, right? But still, it would take an infinite amount of t star, of Bob's time, to reach the horizon. No surprise here because t star is t. T star is the Schwarzschild time. We know it takes an infinite amount of time to reach the horizon according to Schwarzschild time, and the same is true for Bob's time because it is Schwarzschild time. Right, so this is how things look like for Bob, who cannot describe the inside of the black hole in his coordinate system. But what he can do is he can certainly set up light cone coordinates. So let's call the light cone coordinates of Bob u bar and v bar, defined as usual as the difference and the sum of the Cartesian coordinates. And in terms of the u bar and v bar variables, the metric takes the form of du dv, which is the Minkowski metric of light cone coordinates, multiplied with this conformal prefactor, as usual. The point of going to the light cone coordinates is, of course, that in light cone coordinates we can write down the action easily and then solve it and write down the solution to the quantum field theory. Let me remind you of something, though. There is no, this is not a reminder. This is I will later remind you of something to do with that. We have now two coordinate systems, Alice's and Bob's, that are very suitable for certain circumstances. How are they related to another? We only related them to Schwarzschild coordinates, but what is their direct relationship? In terms of light cone coordinates, that's easy to express. Namely, Bob's coordinates u bar and v bar transform into Alice's coordinates u and v one by one. The u bar variable goes into u like this, and the v bar variable goes into v like that. And if you remember from Friday's lecture, this is also the relationship between the light cone variables of the accelerated observer and the light cone variables, the light cone coordinates of the inertial observer. They also had such an exponential relationship. The only difference was that instead of 4m, you had 1 over a. And later we will exploit that similarity. So for now, let's just keep that in mind. That's why it has a two-colored box here. We will need that later on again. That this is the simple relationship between the light cone coordinates of Alice and Bob, where Bob has the barred variables and Alice has the u and v variables. Okay, so for Bob, the action, which always takes this form, takes that form in the case of the tortoise coordinates, t star and r star, and then if he changes his coordinates to the light cone coordinates, then that's the action that he gets. Oh, just before I came at the university, I fixed it. But apparently, I opened the file too quickly before Dropbox could update it here. These u's and v's should have bars, because these are the variables of Bob here. You know what? Let's do some magic. Just close this, and then let's see if I open it again. It's hopefully the new version. No, doesn't look like it. I hope I don't have conflicted copies on it now. All right. Bob can find the solution to the quantum field theory now, because the equations of motion, everything works the same way as it does, frankly, like in Minkowski space. It's the same equation of motion with the same arguments. You can identify what the mode functions are, and so on. So Bob would say, I quantize my field in my light cone variables, or r star, t star variables, and this is what I get. This is the expansion of the field. Where the u, again, it's the u bar here, is t star minus r star. Again, he has right movers and left movers. Bob fulfills with this all the three criteria, namely the equation of motion will be obeyed, the canonical commutation relations, and hermeticity. Now, Bob is using different mode functions than Alice is doing. So his expansion is a different expansion than Alice's, and so he also needs to use different creation and annihilation operators. Let's call Bob's B and B dagger. What is Bob's notion of a vacuum then? So if you ask Bob, which state is the vacuum state for you? Bob would say, well, look, where I am at r going to infinity, the metric is the flat metric. And if my detectors don't click, that's what I call a vacuum. So I would say that the vacuum state is this state, which is the state annihilated by my annihilation operators. Yeah, see, this should be a Bob here. Sorry about it. I don't want to fix it here now, because then I have too many conflicted copies around. Okay. So eventually, we'll have to figure out which is the right state of the quantum field theory. Is it Bob's vacuum, or is it Alice's vacuum? Can I take a poll? Who thinks it's Alice's vacuum that the black hole will be in? Who thinks it's Bob's vacuum? All right, few takers. Nobody for Alice's vacuum? No? All right. But remember, if you go for Bob's vacuum, you're saying there's no Hawking radiation, right? Because it will mean Bob doesn't see the vacuum, right? If the quantum field is in Bob's state, well, if the quantum field is really in the state that Bob would describe the vacuum, it would mean no radiation. So we'll see. I don't want to give it away just yet. You might think, well, okay, so it's got to be Alice's, right? No, that's not the answer either. All right. Okay. So, as I said, I used to never teach black hole radiation because it's just, there's so many things that can go wrong and so many things. I'm trying to tell you only the safe stuff, right? But you will see later on. But I've been to a conference. I was at a conference last summer on black holes. And there were several talks by a group that is aiming to actually see the horizon of a black hole with suitable telescopes. And that convinced me that we'll have to look into this. I mean, it's just time to figure this one out, because we may be able to actually see black hole horizons. So here's what's going on. What convinced me to go into this. This is like a small commercial break until we get back to the technical stuff. Okay, so we want to model real black holes. Okay, here's an example of one, Sagittarius A star. You may have heard of it. It's the central black hole in our galaxy. The astronomers tell us that apparently almost every galaxy has probably a huge black hole at its center. Now, ours is of the smaller kind. It has only about 4 million stellar masses. There are others that are hundreds, even 1,000 times heavier than that. The Schwarzschild radius of the black hole at the center of our galaxy is about 44 million kilometers, which means that if you cross the horizon, you can go for a long time until you get crushed. You could actually do experiments. You could write up your results and all of this. Not that you could tell anybody later outside, but yeah. The black hole is 26,000 light years away from us at the center of the galaxy. Our whole galaxy is like 100,000 light years across. I mean, radius, 200,000 diameter. And so you see where we are roughly on the scale of our galaxy, of the Milky Way. Now, what I found very exciting is that there is this collaboration, the Event Horizon Telescope Array collaboration. Some of the collaborators are here at PI, actually. They have been operating telescopes already for a few years. The aim is to switch together, to link up a lot of telescopes all over the Earth to make measurements of amplitude and phase of radiation that arrives in the millimeter or sub-millimeter range, which is like terahertz. And then to use synthetic aperture. Basically, instead of having a huge lens as big as the Earth, you measure the amplitude and phase with those telescopes distributed over the Earth's surface, have those data all flow into one big computer, and then the computer acts like the lens. The computer calculates what the lens would do with that incoming wavefront. And in this way, you see, the main point of this is not to be able to collect more light. The main point of this is to have a much larger aperture. If you remember, the size of the aperture, the size of the opening of your telescope determines how sharp your image can possibly be. You can think of it in terms of the uncertainty principle. When a photon comes in to your telescope, it has to enter the opening. And as it enters the opening, its position is measured because it's within the opening, right? So you've made a measurement. The measurement was the position of the photon was in the opening, not outside the opening. And that gives you, by the uncertainty principle, an uncertainty in the transversal momentum. But if you don't know exactly how fast the photon goes this way or that way, then you don't know exactly which direction it came from. So for that reason, the smaller a telescope opening is, the more you measure the position of the incoming photon, the less you can know the angle from which it came from. And so a tiny, tiny telescope opening means unsharp image. Larger telescope opening means sharper image. And if you have a telescope that consists of many telescopes that are far away from each other, then you can work with the uncertainty principle and have a really, really sharp image. The aim is to eventually image, and the plan is to achieve that by 2017, to image with an angular resolution that is good enough to resolve that, to resolve 44 million kilometers at a distance of 26,000 light years. That you can actually see the event horizon or whatever might go on there. I mean, obviously, you can only see stuff that falls in, and you can see the shadow that it casts. Lots of modeling at the moment goes into what you ought to see, and then that will be compared with what you do see. I've talked with somebody from that collaboration, and they said that what they see at the moment is not what the models would predict. But it's not, she's not putting it out there yet in a paper. It's not yet confirmed sufficiently securely. But of course, that would be the most exciting thing. If what we see contradicts our models, because then we are bound to learn the most. Anyway, it's all very exciting. So let's look at real black holes. In practice, they will have complicating properties, such as a ring down. A black hole forms, and then it wobbles a little bit until it settles in. That doesn't take very long, usually, that ring down, but it would be there. Black holes would have peculiar velocity relative to us, relative to the CMB, and so on. Black holes would, of course, have angular momentum. They could be charged. And the mass of a black hole can change because it eats up cosmic microwave background radiation at the very least, because it's ubiquitous, always there. But it can also eat up gas clouds, even stars, and so on. So all of this means that the Schwarzschild solution is not really describing it. But for our purposes, let's just forget about all these complications. Let's neglect them all. And let's also assume, very crudely, that the rest of the universe is empty. And in that case, in that approximation, the space-time of a black hole would be described pretty much by a Schwarzschild metric. But there are all these caveats, right? Like the black hole should really be growing or shrinking and moving and rotating and having charges and all that. But if we assume that we have one of those solitary black holes, the rest of the universe is empty, then which state would the quantum field theory be in? Now, in principle, of course, we would have to calculate that by calculating through the process that created the black hole. For example, if it's a stellar black hole, we would have to calculate through the initial conditions of a star, and then it collapses, and then eventually we get out what the situation is after the black hole has formed. All of which would be very difficult because the physics of the stellar collapse is difficult already. But then it involves nonlinear gravity with quantum field theory, and we can't really do that. Not that people haven't tried, but it's very hard. And I will tell about caveats about them a little later. So what state is it then? Could it be that the state of the quantum field theory is what Alice would call the vacuum? Or could it be that the state of the quantum field theory is what Bob would call the vacuum? It turns out it's probably both. And I think it's the first time, and I hope the only time in this course that I have to use the word probably. Because really, as far as we can tell, this is the most plausible answer. It's probably both. Probably the state of the quantum field of such a black hole is what Alice would call the vacuum for the right movers, which is to say for the modes of outgoing particles. And it's probably the state that Bob would call the vacuum for the incoming particles, for the left-going ones. Remember that the total state is the tensor product of the states of each of the modes. So we can easily separate these things, the left-moving modes, one state, the right-moving modes, the other state, right? So mathematically, that's not a big deal. But what's the physics of it? Why would it be the case that the state of the black hole is such that, on one hand, it is annihilated by the annihilation operators of the right-moving, of the outgoing modes of Alice, and it's annihilated by the annihilation operators of Bob as far as the left-moving or the ingoing modes for Bob are concerned. Well, we'll have to study the left movers and the right movers separately. After all, they're independent degrees of freedom. We can study the rationale for both of them separately. Now, one way to arrive at that conclusion would be, as I said, to calculate through the formation of a black hole. And the cleanest way to do that would be to take, let's say, the collapse of a spherical shell of matter or radiation in Minkowski space. So you start out with Minkowski space. You have very far away a sphere of matter, and it's infalling. It's a very symmetric, clean situation. You have vacuum inside, vacuum outside, in just this sphere. And otherwise, Minkowski space just tiny little bit perturbed because there's this mass shell around. And then this thing is infalling, and eventually that sphere is compressed to the extent, is so small, because of the infalling, so small that it disappears behind its event horizon, and we have a black hole. And that can be attempted to calculate that. Now, the math allows you to do it. And there are calculations in textbooks that do that. The trouble is that, and this is how Stephen Hawking did it in the early 70s. The trouble with this derivation of black hole radiation and the derivation of that state is that this calculation involves that you have to allow wave packets to be blue shifted by an infinite amount towards the horizon. And while you can do that mathematically, we do not believe that we understand the physics of that, of blue shifting modes to that extent. Because if you had just one photon of that energy, it would have more mass than the black hole. Planck scale physics must kick in at some point. And so the possibility has been raised for many years that maybe there is no Hawking radiation, because maybe these calculations are wrong. Maybe Planck scale physics kicks in, invalidates Hawking's original calculation one way or the other. And there have been a whole number of studies, it's a whole industry, like hundreds of papers, that studied what happens to Hawking radiation if you assume that quantum gravity interferes in one way or the other with Planck scale physics. And the Hawking radiation has proved itself to be enormously robust. It basically always comes out. And many would say that this is because Hawking radiation is protected. It has to be there for reasons other than just gravity and quantum theory. It has to be there perhaps because of thermodynamic reasons. It seems that black hole thermodynamics ties in naturally with the rest of the thermodynamics of the rest of the world. And therefore, there would be some real trouble with thermodynamics if black holes were not to radiate. But that's a pretty weak argument for deriving Hawking radiation. It's just a consistency argument. It's perhaps making it plausible why the detailed calculations through the collapse are sort of robust. They give you the right answer for the wrong reason, right? So you make assumptions that cannot hold, but somehow things have to work out anyway. Others, pioneered by Bill Unruh and Silke Weinfurner and a few others, have studied hydrodynamic analogs of black holes. You see, when water flows, there's a certain wave equation, and that wave equation depends on the depth of the water. So, for example, if the ground of that water basin has different heights, different places, then the speed of the water changes. Also, if you make the water spin, for example, or flow in some way, then that, of course, will impact the speed and the dispersion of water waves on that. And it was shown that the impact that the profile of the ground and the flow of water can have on the propagation of waves can be very closely matching the effect of gravity, the effect of curvature. So if you have waves on a curved space-time, they can have dispersion, they can have propagation properties just because of the non-triviality of the metric that is in one-to-one correspondence to some extent to the propagation of water waves in suitably arranged water. And you see there in water is a similar thing. You have an ultraviolet cutoff. You cannot have wavelengths smaller than the intermolecular distance, for example. So then the question is, can you cook up a hydrodynamic analog of Hawking radiation, at least the classical part of it, at least the wave part of it, the compression of wavelengths to smaller and smaller wavelengths towards a horizon, in this case, a water horizon. And again, in those experiments, it seems to turn out that there's a huge robustness. It doesn't really matter what the small-scale physics is. The overall hydrodynamics is the one that you would expect for a black hole, irrespective of the short-distance behavior. Anyway, so I didn't want to give you that calculation because it's probably right for the wrong reason, right? So, but still, you should, of course, look up Hawking's original paper of 1975 or something. It's really, I mean, you can see that was a genius at work there. Fantastic paper. Okay, so instead, let's pursue more heuristic arguments, down-to-earth arguments. Let's assume that the rest of the universe has no stars, right? So it's all empty. In that case, when there's a black hole, there is really no reason for radiation to flow into the black hole. There is no source of that radiation. We assume that there are no stars, nothing. So there should be no flux of quanta into the black hole. From that consideration, we deduce that the left moving, that is to say the ingoing modes, should not be occupied. There should not be particles propagating towards the black hole when the black hole is alone in the universe. Of course, if there's another star that shines light on it, of course, that will be ingoing modes that are occupied, right? But other than that, there shouldn't be any, which means that the state of our quantum field should be what Bob calls the vacuum as far as the left-moving modes are concerned. Now, that part is relatively straightforward. Because, I mean, imagine what it would else mean. Bob could be 1 billion light years away from our black hole. Why would he see a flow of particles towards that black hole at the other end of the universe, right? So, no, it should be the vacuum as far as Bob's concerned. Now, could it be that the right-moving modes, which is to say the outgoing modes, are also in the state that Bob would call the vacuum? Now, that cannot be. Let us remember see, this is the old version here. I had to fix this. Just disregard what's written in black here. U bar and V bar are the variables of Bob, and U and V are the variables of Alice. Let's compare them with the variables of the previous lecture, where we had, again, disregard what's in black here, where we had that U bar was a variable of the accelerated observer, and U was the variable of an inertial observer. So what we see here is a very close relationship. Basically, A, the acceleration, plays the role of 1/4m. And we know what the outcome was of the calculation with the acceleration. Namely, we know that the vacuum of the accelerated observer is not a physical state. It's not a state that the quantum field could be in. That was the conclusion of Friday, if you remember, towards the end of the lecture on Friday. We concluded that the vacuum energy density would be divergent. The energy momentum tensor would be divergent as you approach the horizon if the state that the quantum field is in is the vacuum according to the accelerated observer. So if you went out there and you took, you're an inertial observer, you take a detector, or you just measure energy density by measuring curvature, which you can do because of the Einstein equation, then you would find that as you approach the horizon, things would go wild. You would find a lot of excitation of the detector, you would find a lot of fluctuations in energy, and a lot of fluctuations in curvature. So the vacuum state of an accelerated observer is not a physical state. And that's the situation here with what Bob would call the vacuum for the right movers, for the outgoing modes. It cannot be, because this exact same calculation applies as for the accelerated case on Friday, we can conclude that the vacuum state according to Bob would have an infinite energy density, would have an energy momentum tensor that diverges closer to the horizon. And I'm talking about the outgoing mode's vacuum state. As I will explain a little later, the same argument doesn't apply to the ingoing one. But as far as the outgoing modes are concerned, Bob's vacuum would contribute to the energy momentum tensor in a diverging way closer to the horizon. And that has all sorts of problems with it that make us believe that this cannot be the state in which the quantum field is in. In particular, here's a list of the problems. Via the Einstein equation, this would mean that our assumption that space-time is the Schwarzschild solution would be wrong, because the Schwarzschild solution is a solution to the Einstein equation. G mu nu of the metric is equal to T mu nu, where T mu nu is actually vanishing. Right? So that could not possibly be true, because the energy momentum tensor could not even be said to be small. It would instead have to be diverging towards the horizon, so it would invalidate our calculations. Furthermore, and I think that's really a key argument that is not usually made, but I think it ought to be made, is this, that we don't know exactly what happens in the formation of a black hole, but the state that Bob would call the vacuum would be too expensive, energetically too expensive, to survive the collapse or the formation of a black hole. Simply because it would be such high energy. Things have to arrange themselves so that this state doesn't come out. So I think it's dynamically prevented. I mean, the dynamics will be such that this is not going to be the state. If we think for a moment in the Schrödinger picture where the state is time dependent, the dynamics of the state will be such that it will not evolve towards the state that Bob would call the vacuum state for the outgoing modes, because that would be energetically too expensive. Because it's actually divergent. And if the state of the quantum field where the vacuum state according to Bob, as far as the outgoing modes are concerned, then what would Alice see? Now, Alice would be just like an inertial observer observing the vacuum of an accelerated observer. When you go to the horizon of the accelerated observer, you see suddenly a tremendously large energy momentum tensor density. The fluctuations would go very, very large. So in this case, as Alice approaches the horizon, she would see that there is this divergent energy momentum tensor, and she could identify the horizon by being the place where these fluctuations, where the contributions of the energy momentum tensors actually divergent. That would contradict the equivalence principle, because Alice should not be able to tell that when she crosses the horizon, this is what she did. I mean, if she's just enclosed in a flying lab without windows, then locally she's just free falling. The metric is just smooth. Why on earth would there suddenly be this flash as she crosses the horizon? It would contradict the equivalence principle. So what state should the right moving, that is to say the outgoing modes, have to be in? So the question is, what state would the outgoing modes have to be in such that we get a reasonable answer? Namely, such that their contribution to the energy momentum tensor is small, or at least smooth, across the horizon, and such that Alice cannot tell that something special happened at the horizon. So Alice should not see a burst of particles. In fact, she should not see any particles coming from the horizon. Now the answer is that this state fits, of course, the bill. The state that Alice would call the vacuum state for the outgoing modes has these properties. Because remember, in Alice's coordinate system, in those Kruskal coordinates, the horizon is, there's nothing singular there. The metric is just smooth over the horizon. It's absolutely no problem. It's only the Schwarzschild coordinates and, in fact, and Bob's coordinates that are weird at the horizon. But the Kruskal coordinates show, well, it's all fine. And she can do ordinary quantum field theory, left and right of the horizons. No problem for her. When she does the usual quantization, the energy density is just going to be smooth in all of her capital T, capital R coordinate system. Well, and of course, she wouldn't see any particles, at least no outgoing particles, because it's her definition of the vacuum, right? So from that, we would then conclude that the state of the quantum field theory in the presence of a black hole, of a solitary black hole, in an otherwise empty universe, should be the vacuum state as far as Alice is concerned for the right movers, and should be the state that is the vacuum state according to Bob as far as the left movers are concerned. So as far as the left movers, the ingoing particles are concerned, it's Bob's vacuum. As far as the outgoing are concerned, it would be Alice's vacuum. Now let's see. If this is the state of the quantum field, what does Bob see? Because we would be Bob in this. We would be far away, like 26,000 light years away. What would we see? Well, first of all, because of this combination here, as far as the left movers are concerned, as far as the modes are concerned that describe particles that are left moving, which is to say, in going to the black hole, we're in the vacuum state. So we would not see any particles traveling towards the black hole. But as far as particles coming from the black hole is concerned, the state of the quantum field theory would not be Bob's vacuum, it would be Alice's vacuum. So we expect a Bogoliubov transformation, which tells us that Bob sees a flux of particles coming from the black hole. Because as far as the modes of particles coming from the black hole is concerned, it's not Bob's vacuum, it's Alice's vacuum. Now, how much? Well, we can calculate that now. In fact, we've basically already done the calculation. Remember, we calculated what temperature an accelerated observer would see when the state of the quantum field is that of is the vacuum according to an inertial observer. And we now know that that calculation is exactly the same here We just have to rename our variables. And in particular, what used to be the acceleration on Friday is 1 over 4m now. But the relationship between the two light cone coordinates is exactly the same. And the relationship between the equations of motion, all of those things, well, almost, we get to the difference a little later, is the same. I should say that one difference is that when we did the calculation on Friday, the left moving and the right moving modes both did the same thing because both had a horizon. Right? The accelerated observer has both a past horizon and a future horizon. A realistic black hole only has a black hole horizon, doesn't have a white hole horizon. That's why the left and the right movers, the ingoing and the outgoing, are different for the black hole than they are for the accelerated observer. All right, so we know what the temperature was through acceleration. And the temperature for acceleration, that's called T unrho, is given by A over 2 pi. The temperature of Hawking radiation, so the temperature of the radiation that Bob sees coming from the black hole, is then given by, well, A over 2 pi, but the A is actually 1 over 4m. Of course, m indicates the strength of the gravity. But you see an inverse relationship here. So you might have expected that the Hawking temperature would be growing with the mass, because the more mass, the more acceleration, you might think. But it's an inverse relationship, right? So if the mass goes large, the corresponding equivalent acceleration goes small and vice versa. And so similarly, the Hawking temperature is such that it actually diminishes with the mass of the black hole. But that's basically because the horizon is the further out, the larger the mass is. And so the actual acceleration is smaller where you cross the horizon. The surface gravity of a black hole diminishes as it gets larger. Okay, so what we see is that if we are right with the conclusion that the state of a solitary quantum the state of a quantum field on the background of a solitary black hole is this state, then Bob, sitting far away, would see no particles coming from his back, but would see, looking towards the black hole, would see Hawking radiation coming towards him with that temperature here. So his detectors will click as if exposed to a heat bath of that temperature. What would Alice see? Now, as far as the outgoing modes are concerned, the vacuum. So she wouldn't see any radiation hitting her from the front, looking towards the singularity. But she might be hit by some radiation from the back, right? Because that state is not her vacuum state. But interestingly, as far as she's concerned, when she's freely falling into the black hole, she's not running up against any Hawking radiation then. Okay, so here's a quick summary of the relationship then. So here we have the Schwarzschild space-time. Here we have Minkowski space. The accelerated observer is called the Rindler vacuum, and Bob's vacuum is also called the Bulwer vacuum, and they correspond to each other there. Alice's vacuum is called the Kruskal vacuum, and it corresponds to the initial observer's vacuum, which is called the Minkowski vacuum. Now, there are a lot of remarks that one can make. There's no end to this. Maybe just a few. Remember that the state, we ruled out the possibility that the state of the outgoing quanta could be Bob's vacuum, which would be no Hawking radiation. We ruled that out because in that state, the energy density of the quantum field would diverge as you approach the horizon. And yet, for the state Bob left, for the ingoing modes, we said, well, that's okay. That's probably the state of our quantum field. How come the difference there? And let me just remind you of what we just said, what we said a few minutes ago, which is that an accelerated observer has two horizons, right? Future horizon, past horizon. And therefore, the left and the right modes both behave in the same way, and both give you an infinite contribution towards energy density. Sorry, I should say that both the left moving and the right moving modes of the accelerated observer give you an infinite contribution to the energy density. But in the case of a black hole, that's not the case. There's only one horizon, there's only one piling up of the energy, and that's only for the right moving modes, for the outgoing modes of Bob. And that's why it is possible to have the state which is this hybrid between Bob's vacuum for the ingoing modes and Alice's vacuum for the outgoing modes. Finally, just to complete the picture, we dropped early on the angles phi and theta. Do they matter? It turns out, yes, this is not trivial to drop the angles. For one thing, we should have thought so, because in 2 dimensions, gravity has way fewer degrees of freedom than it has in 4 dimensions, and so it's really a different kind of theory. But in practice, it makes life a little more complicated, but not too much. Here's what it does. When you reintroduce the angles, then, so when you consider the true 3+1 dimensional theory, then in order to get started, you need a mode decomposition again. You need to decompose your field into modes that obey independent harmonic oscillator equations. So you have to uncouple the Klein-Gordon equation. And the best way to do that, given the symmetries of the Schwarzschild solution, is to use, well, in principle, we would use Fourier transform, right? That turns the Laplacian into a multiplication operator, and so we get the partial differential equation decoupled into lots of ordinary differential equations. But because we have this rotational symmetry here, the analog to Fourier transform is the decomposition in spherical harmonics. So we do the decomposition into spherical harmonics, and then the Klein-Gordon equation becomes this Klein-Gordon equation. It's the D'Alembert for the 2 variables of space and time that we always worked with. And then we get this additional term here that stems from the angular degrees of freedom, where L and M are the quantum numbers of the spherical harmonics. Now, even when L is equal to 0, we have a contribution here. So it even differs for the S wave, for the no angular momentum case. It's still a difference to the case that we considered so far, where there was just no contribution from the angles. So whatever angular momentum we are looking at, whatever angular momentum mode we are looking at, there's going to be what looks like a potential. If you hold L fixed, and you remember the whole point of this was to decouple the degrees of freedom. So for every L, we have separate degrees of freedom. If you hold L fixed, then you get what is effectively like a potential in the Klein-Gordon equation. It's some function of R. So it is as if you had a Klein-Gordon equation with a potential, and it turns out that that potential peaks outside the horizon. And what that means is that the Hawking radiation has to make it across that potential. Now, the high frequency part of it will have it easy. The lower frequency part will have it a little harder to come out of it. But basically, the upshot of this is that the Hawking radiation would still be there, but it would be modulated by what is called the gray body factor. If, for example, you have an object that is black and you heat it up, then you get black body radiation. But if you have an object that is blue or red and heat that up, then you get a modulation, right? And so similarly, the black holes would be having a slightly distorted spectrum, would have, you know, a little less flux of Hawking photons out because the Hawking radiation needs to make it across that potential there. Now, that's basically it for this lecture today and for the course. If you are further interested in the black holes business, I can point you to a talk that I gave when I gave the opening lecture to the Black Holes Conference last summer. And I summarized there in simple terms, first a little bit about the history of black holes, and then the so-called firewall paradox. So I haven't been able to find the video recording of it. I'll try to dig it up because all those talks have been video recorded, but I will link to the slides at least of that. And I suppose you're now ready to enjoy that. Enjoy it. Okay, well, there is one more lecture that unfortunately we are out of time. This is the last day of classes this term. But I prepared one more lecture which is on quantum field theory with interactions on curved space in terms of the Feynman path integral. So how do you derive Feynman rules and all of that? I've linked to the lecture on our homepage. The video recording of 2 years ago should not be too bad. So if you want to look that up. Okay, so there are a few more links to come. And other than that, thank you for coming. And let me know if you have questions. Thank you. Yeah?
When we discussed the state of a black hole, why do we prefer the vacuum state rather than excited states?
Well, you could consider excited states, and in fact, in practice, the universe won't be so clean. There's always stuff around, and in fact, it sharpens our argument. For example, when we say that the vacuum state of Bob for the outgoing modes would be having a divergent vacuum energy towards the horizon. Well, in fact, if there were particles, each one of those particles would also have a tremendously much elevated energy there. So it sharpens the argument, it makes the argument stronger.
And finally, what about the difference regarding the horizons? That the accelerated one has two horizons and the other one has one horizon? I mean, we still we identified the acceleration with 1/4m besides that fact, right?
Yes.
How is that?
Oh, remember that okay, so here it is. Here's the relationship between the accelerated and inertial light cone variables, the V's and the U's. And in the case of the black hole, I gave you only one, but of course there's a V version of that too. So in principle, if you were to extend the Minkowski's, if you were to extend the Schwarzschild solution to its maximal extension, so that you have both types of horizon, black and white, then the symmetry of the two examples would be complete. And you would have to conclude that Bob's vacua are just no good in any case, not ingoing, not outgoing. But the two considerations for the black hole and for the white hole horizon, corresponding to the future and the past horizon of the accelerated observer, are really separate stories. There's one story for the U, which would be the outgoing modes, and there's one story for the V, which is for the ingoing modes, and the story for the V just doesn't carry forward from the accelerated case to the black hole case. But they're really separate issues, but they are related in the same way. If you look at this equation here, the A corresponds to 1/4m. If you look at the V, it too has A is equal to 4m. So these are independent considerations, but both have the same temperature relationship. So just because one doesn't doesn't carry over, doesn't invalidate the observation that for the other, the relationship is A goes to 1/4n. Natasha?
So in order to have either the Hawking radiation or the window effect, we needed to put a scalar field coupled with gravity. And my question is how realistic is that? Because everybody seems to be willing to observe Hawking radiation, or we don't see Hawking radiation just because the temperature is way too small. But how is it really a scalar field feeling this? And if that's the case, what is it?
So the claim is that a similar calculation can be carried out for all kinds of fields that are in the standard model. And the calculation is usually done for a scalar field just because it's the simplest to carry out the calculation. That's a different motivation from cosmology, where in cosmology we have positively a reason to look at the Klein-Gordon field, and that's because its potential can trigger inflation, whereas an electromagnetic field could not trigger inflation, and neither could electrons trigger inflation. They don't contribute to the energy momentum tensor in the right way. So there was positively a reason to consider scalar fields. But in the case of black holes, Hawking radiation would be consisting of all sorts of particles that nature has. And so the idea is that you have a thermal spectrum of electrons, of quarks, of every species. For every species, you would get a similar, you would do a similar calculation. You would have slightly different gray body factors, but in principle, it's the same temperature for each species. So scalar in this case, just because it's the simplest. Yeah, see?
So when we consider the process of evaporation of black hole, because of the inverse relationship between temperature and mass of the black hole, that means the black hole, as it gets smaller, the radiation is faster.
Gets hotter, yeah.
Does that mean that as the black hole shrinks in size, as it evaporates, there's some acceleration?
Yes, that's right. So there's a critical size of a black hole, and if a black hole is larger than that size, then it's going to grow in our universe. And basically, that size is given by the typical wavelength of microwave radiation. So you see, the cosmic microwave background has the bulk of its radiation at wavelengths of a few centimeters, microwaves. And if you have a black hole, I didn't show you here, but the black hole radiation has a thermal spectrum, as we deduced by analogy to the, by appealing to the by just redoing the calculations recruiting the calculations of Friday, has a temperature, and that temperature has a peak. It has a spectral distribution, and the peak of that distribution is at wavelengths which correspond to the size of the horizon. So if you have a black hole of 55 million kilometers radius, like Sagittarius A star, then the Hawking radiation that you expect from that black hole has a black body spectrum where most of the photons, the peak of the distribution, are emitted with a wavelength of about 55 million kilometers. And you can imagine how cold that is, right? When the wavelength is that large. Consider, for example, the 6,000 Kelvin light from the sun. 6,000 Kelvin light from the sun has a typical wavelength of a few hundred nanometers. Like green is what, 600 nanometers or so, 500, 600 nanometers or so. So that is, so short is the wavelength at 6,000 Kelvin. If you have a wavelength of 55 million kilometers, the temperature is enormously small, which means that a galactic-sized black hole is just not going to evaporate because it's going to absorb way more energy from the cosmic microwave background than it can absorb. It is, you see, it is colder than the cosmic microwave background. And if a black hole is smaller in size than a few centimeters, just a sec, if it's smaller in size than a few centimeters, then it is hotter than the CMB, which means that on balance, it is absorbing CMB radiation, but it's emitting, because it's hotter, it's emitting more. So it actually shrinks. And so it shrinks, 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 and you can calculate the differential equation that governs that. And it should go with a bang, because, yeah, as it gets smaller, it gets hotter, it shrinks faster and faster, and nobody can calculate the bang itself. Nobody knows what happens there. Is, for example, all the information liberated again that was in there, or not? That's, of course, the big question in black hole physics. Will unitarity be violated by black holes or not? If a black hole forms, absorbs stuff, and then evaporates completely, then we have an initial state without a black hole, we have a final state without a black hole. The question is there unitary evolution between them? That is what the big debate is about nowadays.
So obviously this wouldn't be a large contribution, but if we were to do these calculations with allowing all kind of fields to be excited, like at what point, like what, is it just a few, like maybe 8 order of magnitude hotter available, just because there's so many other fields that could potentially excite other than just the like single scalar field, or is it the same temperature? What would be the?
Oh, it's the same temperature for all of them.
But like, so do each of the fields contribute individually because they each can bleed off energy?
Yeah.
Yeah,
that's the idea.
Right.
Yeah, I mean, there are of course fields that cannot be separated, that just strongly interact. For example, gluons self-interact very strongly, and so or gluons and quarks, there is very strong interaction, and so it's, of course, it would be bad. It would be a bad perturbative approach to say that there's a gluon radiation and then there's a quark radiation. No, that has to be done together. But whenever you can do a perturbative approach, then yeah, it would be independent radiation. Yeah.
So we said that Alice, that is near the black hole, will feel radiation in her back.
Sorry, is she what?
Will feel particles coming from
the back, yeah,
the back,
that's right.
And Bob will feel particles coming from the horizon. So what about an observer that wants to go from infinity to the horizon? At some point you will have to, because it will, Bob's calculation will hold, Alice's calculation will hold whenever he is in these two positions. But dynamically, he will fall, he will like go to the horizon, and at some point he will.
Oh yeah.
And what is that? Is that relevant?
Well, in order, see, these studies are best done with on-the-way detectors. You let them fly towards a black hole and see whether they get excited. Because in this study, as we did it today, the advantage is that the framework is sort of just quantum field theory. We never had to appeal to first quantization. But the disadvantage is that the modes that Bob used and the modes that Alice used are really very non-local things, as modes always are. And so when we say that there are particles or there are not particles, then it's in a certain mode, it's always a very non-local statement. In order to extract local information, you either have to create wave packets and see how they propagate, which is a difficult thing to do, or you have to appeal to on-the-way detectors and couple them to the field. It's very difficult to extract local information. But maybe let me point out something that is very much related to what you said, and it shows how non-trivial this new state has to be arrived at. You see, we made no attempt here at explaining how that state is being arrived at. That's, of course, a huge challenge, but it probably takes quantum gravity to actually dynamically, convincingly prove that this is the state that we arrive at. Consider, for example, the case where we would have done that same argument here, but it wasn't a black hole. It was just a neutron star. So in that case, what's different? Now, we can no longer appeal to the argument that Bob's vacuum is contributing a diverging amount of energy momentum towards the horizon, because there is no horizon. It's a neutron star. It's bigger than its Schwarzschild horizon. So we have the Schwarzschild solution outside the neutron star, but inside it's different. And it's not Schwarzschild, and there is no singularity, and there's no horizon. Everything is just regular. So in that case, you would expect that the vacuum is Bob's vacuum all the way. So what must happen is this, that if you take a neutron star, and which is to say, it's the Bulba vacuum, right? Both for the, when I said all the way, what I meant was for the ingoing and for the outgoing modes. Now imagine that you feed that neutron star. So you throw matter towards it. That doesn't make it bigger, it makes it smaller, right? Because it becomes heavier and it contracts. Now imagine you throw high density stuff towards the neutron star and it makes it shrink, 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 shrink. Eventually it disappears behind its horizon. Now suddenly these arguments kick in and we must have this non-trivial vacuum with outgoing Hawking radiation and all of that. I imagine that what's going on is that there is a transition. Basically, as the neutron star shrinks towards its Schwarzschild horizon, the Bulba vacuum, the vacuum of Bob, becomes less and less tenable because the energy density doesn't quite diverge yet at the site where the neutron star kicks in, where it starts, but it becomes larger and larger. It's not diverging, but it becomes larger and larger. And as the neutron star shrinks, there will be more and more energy. And so energetically, that eventually becomes too expensive. And so the Bob's vacuum for the outgoing modes is less and less tenable, and it would become more and more like Alice's vacuum. So I think there's got to be a smooth transition. I don't know about smooth, but there's got to be some transition that hopefully can be calculated of the vacuum when we just have a star to the vacuum when we have a black hole. And I imagine that the cleanest way to derive that would be on the basis of energetic considerations. So, for example, maybe following up on your intuition there, imagine you have an Unruh-Dewitt detector. If you remember lecture 8 when we first did the Unruh effect. What we said is this. Acceleration radiation, what we said in that case was that the Unruh temperature can be interpreted as arising in this way. When you have a detector, and that could be just a hydrogen atom, or some quantum system that has a charge in it, like an electron. If you have a detector that's on an accelerated path, then the charge that's within it is accelerated. And accelerated charges radiate. Now, why does it have a charge? Well, if it didn't have a charge, it wouldn't see the field. So there must be charges in there. Okay, so if you have an accelerated detector, you must have an accelerated charge. An accelerated charge excites the field, emits photons. But now you have two quantum systems interacting with each other. You have the detector quantum system interacting with the quantum field in such a way that the quantum field gets excited. No wonder that this interaction also goes the other way, and the field excites the detector. And that is then interpreted as the Unruh radiation. Now, this acceleration can have different reasons. The acceleration of the detector could be because you attach the string to it and you're pulling really hard on it. So that's why it's accelerating. But the detector may also be accelerated because it's freely falling towards a star or a black hole. So for example, if you have a charge or a detector orbiting some object because it is either gravitationally bound or because it is attracted with electrostatic forces or whatever, then it's orbiting like an electron around the proton. It's an accelerated charge, it radiates. Well, until it reaches the lowest Bohr orbit, right, in the case of the hydrogen atom. But now imagine you have an non-relativity detector and you let it fall freely towards a black hole. And a little bit to the side, you have another non-relativity detector and you have it freely falling towards a star. It's not quite formed a black hole yet. Then what should that non-relativity detector observe? If you couple it to the outgoing modes, meaning you have an non-relativity detector which has a closed, it has an enclosure, but one side is open, the side that's facing the star or the side that's facing the black hole. So if you're just sensitive to the outgoing modes, let's say. Now, if that thing is freely falling towards the star, we have a freely falling, therefore accelerated charge. Therefore, it should radiate. And therefore, the quantum field should backreact on the detector, make it excited. So we might expect that the freely falling detector towards a star would both radiate and click. And that's the answer that you get if you calculate that on the background of the Bulber vacuum, which is the vacuum that's Bob's vacuum when it's just a star. But then, if that star has turned into a black hole, then it's Alice's vacuum. And Alice doesn't see particles. The detector wouldn't click. It's a weird thing. See, so basically, Alice could tell whether she's falling towards a black hole or a star by checking for the absence or presence of Hawking radiation, but in the reversed way. Because falling towards a star, her detector would click. Falling towards a black hole, her detector would not click. If, on the other hand, she hits the brakes, or her spaceship is caught with a lasso and held in place, so it's hovering above the star, or it's hovering above the black hole, then it's the other way around. Because then she sees Hawking radiation when she's at a standstill, when she's hovering over a star, and she sees no radiation if she's just hovering. She sees Hawking radiation when she's hovering over a black hole, and she sees no Hawking radiation when she's hovering over a star. But then if you cut the cord and let her fall freely, it's the other way around. Yeah, it's weird. And especially that transition. If a star becomes a black hole, then the vacuum state must change, right? And so there must be, I imagine, some sort of wave that goes out there, as the vacuum changes. It's basically the Hawking radiation starts being emitted, and so there's a front of Hawking radiation that first goes out. But you should have seen the conference last July. People just couldn't agree on anything. Seriously. I mean, not only were there people who said that Hawking radiation is this way and others said, no, it's the other way. No. There was a significant group of very prominent people saying, what? There is no Hawking radiation. And then there were people who were saying, what? There are no black holes anyway. Yeah, and everybody had really good arguments too. Yeah, so in principle, I would have just thrown up my hands and said, oh, who knows? I mean, this just has to await quantum gravity. But since these experiments are coming up, where we may be able to see the horizon, right? It just means we really ought to understand this better. It's very unlikely. I mean, basically, out of the question that you would see Hawking radiation, because, we would have to observe wavelengths, photons of a wavelength of millions of kilometers. You know how much energy they have? It's just nothing. And forget it. It's extremely cold. So we're not going to observe galactic or even stellar black holes Hawking radiation. For a stellar black hole, for example, our sun has a Schwarzschild radius of about 3 kilometers. Our sun is not going to turn into a black hole. Heavier suns will. Or are turning into black holes, and they have then radii of a few more kilometers. But that means that their Hawking radiation has a peak wavelength. I mean, the peak of their Hawking radiation would be at wavelengths of several kilometers, which is very low energetic. In other words, very, very cold. And so there are many other temperatures that far exceed that. For example, the CMB at 3 Kelvin.
So our best bet is like something that's going to be microscopic.
Yes, yes. There could have. I mean, it could be that at CERN black holes would be created, or that cosmic radiation might create black holes. In fact, we should not worry about creating black holes at CERN, because the cosmic radiation is way more energetic. And so if there was a risk at CERN, there would be a much larger risk with the atmosphere because of the cosmic radiation being much more energetic. And in any case, these black holes would be way smaller than centimeters. They would, decay pretty quickly. They would be just like a special kind of particle. And in fact, it's been studied what kind of signature they would leave behind. They would basically, it would look like a particle is being created, and then pop, it explodes into a set of other particles, which is just the evaporation process in this case. Possible signatures of that have been calculated. Yeah.
So those models that try to look at that, what do they expect the outcome to be? Because this kind of comes down to the information paradox. So if what goes in doesn't come out.
Well, in principle, it could be that the S matrix for such processes is not unitary. That could be, yes.
So like, what kind of predictions are they making?
I don't know. I suppose, if you're prepared to violate unitarity, then really the doors are wide open. You can get all sorts of things. Yeah. Yeah, so the firewall paradox, if you're interested in that, is basically saying that something's got to give. It's either unitarity or the equivalence principle. Or we don't understand at all how quantum field theory works. It's going to be one of these. Yeah. And the equivalence principle seems pretty deep, and so is unitarity. But it seems we can't have both. Right?